at latitude 62 degrees north, situated in the volatile stretch of ocean between Norway and Iceland, lies the Faroe Islands archipelago. In 2014, this remote location became the site of a significant shift in marine engineering led by a company named Ocean Rainforest. While most aquaculture remains in sheltered bays, this enterprise deployed an industrial-scale seaweed cultivation system directly into the high-energy environment of the North Atlantic Current. The physical parameters of this location are severe. The cultivation site is subjected to average wave heights ranging from 6 to 8 meters and constant water currents flowing at speeds of 2 knots. Historically, local fishermen and aquaculture engineers avoided placing permanent structures in these specific offshore zones because the kinetic energy generated by winter storms is sufficient to destroy standard rigid fish cages and snap heavy steel cables. Despite operating in waters previously deemed unsuitable for agriculture, the project has defied structural failure to achieve commercial viability. By 2024, the facility was successfully harvesting hundreds of tons of sugar, kelp biomass annually. This consistent performance attracted significant global attention, resulting in a $6.2 million series of funding round in 2023 led by the World Wildlife Fund and Builders Vision. This capital is now being used to expand operations from the North Atlantic to the Pacific coast of the United States. This success presents a compelling engineering paradox. How does a man-made structure survive over a decade of brutal Arctic winters, where other marine infrastructure fails? And how does this system generate reliable profit from nothing but seawater, without requiring a single square meter of arable land or any chemical fertilizer? To understand the engineering behind this survival, we must look beneath the surface at a patented design called the Macroalgal Cultivation Rig. Unlike traditional fish farms that use rigid plastic circles floating visibly on the water, this system is engineered as a submerged, flexible web that covers hectares of the ocean. The construction begins at the seabed, at depths ranging from 50 to 100 meters. Here, engineers drill steel screw anchors directly into the basalt rock or deploy massive concrete gravity blocks. These are the only rigid components of the entire system, designed to hold the farm in place against the immense pulling power of the North Atlantic currents. Connected to these anchors is not a steel frame, but a grid of high-strength synthetic fiber ropes suspended roughly 10 meters below the surface by specialized buoys. This specific depth is a critical calculation, as it positions the main infrastructure just below the turbulent zone where waves break and release their most destructive energy. Hanging vertically from this submerged ceiling are thousands of cultivation lines, creating a dense underwater forest where the seaweed attaches and grows. The brilliance of this design lies in its refusal to fight the ocean. A standard rigid structure would face a catastrophic spike in tension when hit by a 6-meter wave, eventually snapping under the load. However, because this rig is built entirely from flexible ropes, the entire geometry of the farm deforms in real time. When a storm surge hits, the structure moves in synchronization with the water column rather than resisting it. Operational data confirms that this flexibility reduces the drag force on the equipment by approximately 60% compared to static structures, effectively allowing the farm to absorb the kinetic energy of the storm and protect the crop until the harvest season arrives. The sophisticated tension grid described previously serves a singular purpose: to support the growth of a specific organism known as Saccharina latissima, or sugar kelp. Ocean Rainforest selected this species not for its aesthetics, but for its high tensile strength and aggressive growth profile in sub-zero environments. Biologically, sugar kelp is a cold water specialist. While terrestrial crops go dormant in freezing temperatures, this algae achieves its optimal photosynthetic efficiency in water temperatures ranging between 6 and 11 degrees Celsius. It transforms the freezing North Atlantic water from a liability into a high-yield incubator. The production cycle begins on land, inside a sterile hatchery environment that contrasts sharply with the chaotic ocean outside. Here, technicians induce mature wild kelp specimens to release millions of microscopic spores. These spores are settled onto spools of thin twine, known as seed lines, which are wrapped around PVC cylinders. For a period of approximately 6 weeks, these spools are incubated in tanks with strictly regulated light spectrums and water flow. This controlled start is critical engineering. It ensures a uniform crop density that nature cannot guarantee. The transition to the open ocean occurs in late October. This deployment schedule creates a strategic paradox. The farming season begins exactly when the northern hemisphere winter makes human activity most difficult. Specialized vessels navigate to the rig sites to install the seeded twine. The process utilizes a mechanical applicator that helically wraps the thin, spore-covered string around the thick structural ropes of the MACR system. This effectively inoculates the farm with millions of juvenile plants just as the environmental conditions become most hostile to humans but most beneficial for the kelp. During the dark winter months, the North Atlantic undergoes a physical phenomenon known as vertical mixing. As surface water cools, it becomes denser and sinks, displacing nutrient-rich water from the deep ocean, which then rises to the surface. This upwelling floods the cultivation zone with high concentrations of dissolved nitrates and phosphates. On land, a farmer must purchase, transport, and spray synthetic fertilizers to provide these elements. In the Faroes, the ocean currents deliver them for free. The kelp, having no root system, absorbs these nutrients directly through its fronds. It acts as a massive biological filter, stripping carbon and nitrogen from the water column and converting them into solid biomass at a rate that accelerates as the days lengthen in spring. By April, the fronds can grow several centimeters per day, powered solely by the dissolved gases and minerals in the seawater. The harvest window is dictated by a strict biological deadline, typically opening in May and closing by late June. This timing is critical because of biofouling. As the water temperature rises in midsummer, planktonic activity increases, and organisms like bryozoans and small snails begin to colonize the kelp blades. To secure a premium, food-grade product, the biomass must be removed before this infestation occurs. To execute this harvest at an industrial scale, Ocean Rainforest deploys a specialized shallow draft catamaran. This vessel is designed to straddle the submerged cultivation lines. The operation is a display of heavy mechanical efficiency. A hydraulic arm lifts the main cultivation rope out of the water, revealing a massive wall of brown biomass. At this stage, individual kelp fronds often exceed 2 to 3 meters in length, with a density reaching upwards of 10 kilograms of wet biomass per meter of rope. The rope is fed through a mechanized cutter on the deck. Rotating steel blades strip the kelp from the line, separating the valuable plant matter from the structural gear. The biomass falls into bulk storage containers, while the cleaned rope is immediately spooled for reseeding next season. This continuous loop system allows a small crew to process tons of raw material per hour, effectively harvesting a forest that hangs suspended over the abyss. As the harvesting catamarans dock at the processing facility in Kaldbak Fjord, the operation races against biological decay. Sugar kelp begins to degrade within hours of leaving the 6 degrees Celsius water, necessitating immediate stabilization. The production logs from the 2023 and 2024 seasons confirm that Ocean Rainforest is now landing over 200 tons of wet sugar kelp per harvest cycle. This industrial volume was the decisive metric that moved the project beyond a pilot phase and secured their commercial contract to supply biomass for the United States Department of Energy in the Santa Barbara Channel. Upon offloading, the workflow splits into 2 distinct revenue channels. The highest quality fronds are directed toward the human food market. These undergo a freshwater rinse to remove sea salt before entering industrial convection dryers. The physics of this process are brutal but profitable. It takes approximately 10 kilograms of wet harvest to produce 1 kilogram of dry product. However, this weight reduction concentrates the value. The final dried sugar kelp retails in European specialty markets for upwards of 40 euros per kilogram. This price point is nearly 10 times higher than terrestrial organic spinach, driven by the crop status as a zero-input superfood rich in iodine and magnesium. Biochemically, Saccharina latissima is a nutritional powerhouse that outperforms terrestrial crops. It absorbs trace minerals directly from the ocean, resulting in calcium levels exceeding dairy milk and iron concentrations surpassing spinach by weight. However, its premium market value is defined by flavor. To survive the freezing North Atlantic, the plant produces high levels of mannitol, a natural sugar alcohol acting as biological antifreeze. This evolutionary adaptation creates a distinctively sweet taste profile, devoid of the brackish bitterness found in warm water varieties. When combined with natural glutamates, it offers a potent umami depth, allowing chefs to enhance savory dishes while significantly reducing sodium intake. The secondary biomass stream targets the livestock industry through a preservation method known as ensilage. Rather than consuming energy to dry the kelp, the wet biomass is sealed in anaerobic tanks to ferment, utilizing the natural lactic acid bacteria present on the plants. This creates a stable, long shelf life feed for cattle. The economic driver here is environmental compliance. When integrated into dairy rations, bioactive compounds in the kelp have been shown to inhibit methanogenesis in the rumen of the cow. This effectively positions the feed not just as nutrition, but as a carbon credit tool that allows beef and dairy producers to lower their methane emissions by significant margins to meet strict EU climate regulations. Beyond the food chain, the crop is processed as a raw material for the chemical industry. The cell walls of sugar kelp are rich in alginate, a natural polymer that competes directly with petroleum-based derivatives. Manufacturers extract this substance to create biodegradable packaging films that dissolve in water. Unlike corn-based bioplastics, which require vast tracts of farmland and freshwater to produce, this marine alternative requires no terrestrial resources. The ultimate financial advantage of this model is found in the operational ledger. To generate this multi-million-dollar portfolio of food, feed, and polymers, Ocean Rainforest spent zero currency on arable land, zero on freshwater irrigation, and zero on synthetic fertilizers. The ocean provided the real estate, the North Atlantic Current provided the water, and natural upwelling provided the nutrients. This allows the company to convert the passive kinetic energy of the sea into a high-margin commodity. Despite the high margins and low input costs, this operation carries inherent liabilities that strictly limit its expansion speed. The primary risk remains the unpredictable violence of the North Atlantic. While the flexible tension system effectively dampens wave energy, it is not invincible. A statistical 100-year storm event could generate kinetic forces exceeding the tensile breaking point of the synthetic lines, potentially resulting in a catastrophic loss of infrastructure in a single night. Additionally, the biological risks are acute. The farm operates on a razor-thin thermal margin. If ocean temperatures rise prematurely due to climate anomalies, biofouling organisms can colonize the crop weeks before the scheduled harvest, rendering thousands of tons of sugar kelp commercially worthless for human consumption. However, from an environmental perspective, the audit reveals a net positive impact that contrasts sharply with other forms of aquaculture. Unlike salmon farming, which introduces nitrates and organic waste into the water column, sugar kelp cultivation is restorative. The farm functions as a massive biological filter, absorbing dissolved carbon dioxide and effectively reducing local ocean acidification. This creates a chemical halo effect that benefits surrounding marine life. Underwater surveys indicate that the submerged grid acts as a floating artificial reef, providing a nursery habitat for juvenile fish and invertebrates that would otherwise be exposed to predation in the open water. Looking beyond the specific geography of the Faroe Islands, the validation of this engineering model unlocks vast new territories for global food production. Most coastal nations possess exclusive economic zones that extend 200 nautical miles offshore. Yet these areas remain agriculturally barren because they were previously considered too rough to farm. The success of the hydrodynamic tension design proves that high-energy coastlines from the jagged shores of Chile to the turbulent waters of Tasmania can now be converted into productive sugar kelp fields. It signals a fundamental shift in strategy, moving humanity away from a reliance on exhausted terrestrial soil toward a blue economy where the open ocean is viewed not as a barrier, but as a cultivated field. This leaves us with a final question for you. As arable land becomes scarcer and fresh water becomes more expensive, is the future of our food supply floating in the middle of the ocean? If you found this technical analysis of extreme agriculture valuable, make sure to hit the like button and subscribe for more deep dives into the engineering systems reshaping our world. Thank you for watching, and I will see you in the next video.